This is section 7.5, and this is our last major new technique for integration. It's a technique called integration by partial fractions. It'll actually give us a procedure for what we call a decomposition for a rational function into simpler rational functions that will be easier to integrate. Essentially, this is the idea. In pre-calc, we learned or reviewed how to add two algebraic fractions, right? You would have had to have gotten a common denominator here. You would have multiplied this one by x plus 3 over x plus 3. And you would have multiplied this one by x minus 2 over x minus 2 to get that LCD. And then the x minus x would be 0, and 3 plus 2 gave us the 5. So you learned how to add those algebraic fractions. The goal of the partial fractions decomposition is to actually go backwards. It's to start with this and figure out what these values must have been before they were added. Again, what's the purpose of doing this? Well, remember, we're trying to integrate. What's easier to integrate? This or this? It's always easier to integrate a sum or difference than it is a product. So, why? Because it's easier to integrate. Okay. The bottom of this page contains a whole list of steps for the partial fractions decomposition. It's there for you should you need it, but I think it's easier to follow if we just sort of dive right in and start doing one. But again, the steps are laid out there for you if you want to go back and refer to them at some point. So we're going to start out here, example 1. There is my function that I want to integrate. It is a rational function. This always works with algebraic fractions. And I really want to work with ones where the denominator is factorable. We've already talked about the fact that if it's not factorable, completing the square is the way to go. But this one I can see I can factor this denominator. So let's go ahead and do that. That would be x plus 3, x plus 1. All right, here's my factored form, algebraic fraction, and I'm now going to do the partial fractions decomposition. I'm going to take this fraction and say I would like to make that into two separate fractions, one with a denominator of x plus 3 added to another one with a denominator of x plus 1. And I need to figure out what goes on the top there. Since I don't know yet, I'm just going to call them a and b, and I'm going to try and solve for a and b. All right, like any rational equation, to solve it, I'm going to clear the fractions. I'm going to multiply both sides by the LCD, x plus 3, x plus 1. And on the left, everything just cancels out, and I end up with just the x plus 2. On the right, in the first fraction, I can reduce the x plus 3's, and I'm going to get a times x plus 1. Plus, in the second fraction, those x plus 1's would divide out, and I'll get b times x plus 3. Go ahead and multiply out the right-hand side there. There we go. And now this is sort of the crucial new step. Up till now, everything's pretty much stuff that you learned in algebra, right? Here's what we're going to need to do to solve for the a and the b. I'm going to need to take this single equation and turn it into a system of equations. And the way I'll do that is by thinking about the variables separately from the constant terms. So I'm going to start by thinking, what can I say about the x terms? Well, on the left, there's just one x. But on the right, I have a plus b x's. Now what about the constants? On the left, we've got 2. And on the right, I've got a plus 3b. That gives me a system of equations to solve. And you can do that in multiple ways. Most of these aren't that difficult to solve by hand, but I'll also remind you that if you've got that nice PolySimult app on your calculator, beginning here in Apps, that purple Apps button, my PolySimult, and I want option number 2, the simultaneous equation solver. I do have 2 unknowns and 2 equations. So up here everything looks good. Equations 2, unknowns 2. I'd like fraction form. Everything else looks good. And I do have to be careful how I put this in. The coefficients of the variables go on the left. So this is 1a and 1b equals 1. And whoops, something's not right there. Let me go back one more time. Oh, whoops, I read it wrong. I thought I only had 2 equations. I have 3. There we go, 2 equations and 2 unknowns. That looks better. All right, 1a, 1b equals 1. And then the next one, 1a plus 3b equals 2. And then I can just say solve. And in this particular case, both variables, the a and the b, are both 1/2. Now, if you don't have a calculator that does that, or if you just prefer it, you can also solve by hand, right? Simultaneous equations like this, for example, you could just multiply the top equation by -1 to get the a's to cancel, and you could solve that way. I don't care how you solve your equations, by hand, by calculator, whatever works for you is fine. All right, so what have I got? I can now rewrite my integral. Instead of in this form, I can write it in that form. So I'd have the integral of a, which is 1/2, over x plus 3 dx, plus the integral of b, which is also 1/2, and that's over x plus 1 dx. Those are relatively simple to integrate. I've got the constant multiplier of 1/2. And then if you imagine that x plus 3 being the u, that's just 1 over u, right? And du would be dx. So I'm going to end up with the natural log of x plus 3. Plus, same idea over here, 1/2 the natural log of x plus 1 plus c. And there we go. One quick comment. If you do examples like this or problems in the book, they will often do algebra at the end. I don't require it. An answer like this is perfectly fine, but I'm just going to make a little note to us. If you applied the laws of logarithms to this, I could factor out the 1/2. And then this, as the sum of logs, I could put that together using the product property. The natural log of x plus 3 times x plus 1. And then I could even take that 1/2 and bring it up in the exponent using the power property. So sometimes what you might see is this written as the natural log of, the 1/2 power is actually the square root. And if I multiplied this out, that would be x squared plus 4x plus 3. And then I got my plus c. Now again, there's nothing wrong with this answer, although there is a certain elegance in that one. However, if you do a problem in the book, you're likely to see the grad student who wrote the answer key showing off a little bit, and they very well might write the answer like this, and you'll think you're wrong, even though you actually didn't do anything wrong. I'll try and point those out when we come across them. All right, let's try example 2. Same basic idea. Let's think about the factoring on that denominator for a moment. If I pull out an x first, I would have 2x squared plus 3x minus 2. Let's see if I can guess this. 2x squared is going to be 2x times 1x. 2 is going to be 1 times 2. Make that one positive and that one negative. That's 4x minus 1x is 3x. Of course, you can go through the slightly longer method of the product and sum if you want to. I'm just trying to get us down to what we need here. All right, so if I want to rewrite this fraction using the idea of partial fractions, this time I'm going to have to use 3 fractions. Something like a over the first factor, which is just x, plus b over the 2x minus 1, plus c over the x plus 2. We'll go ahead and I'm just going to write it as one giant multiplication here. We'll multiply everything by the LCD. To clear the fractions. And on the left side, all of that cancels with all of the denominator. So I just get x squared plus 2x minus 1. On the right, with the a, the x's would cancel. So I would get a times 2x minus 1, x plus 2. For the b, the 2x minus 1s are going to cancel, so that'll be multiplied by x plus 2. And the c, when the x plus 2's cancel out, I would get 2x minus 1. All right, some algebra to do here. Let's see, just to speed things along a little bit and conserve my space, if I were to multiply these guys together, that would give me that 2x squared plus 3x minus 2, right? It's just this again. So when I distribute the a, 2ax squared plus 3ax minus 2a. Distributing the bx will give me plus bx squared plus 2bx, and then plus 2cx squared minus cx. Lots of algebra in these problems. All right, we're going to do something very similar as we did to what we did last time, but this time there are 3 types of terms. X squared terms, x terms, and constant terms. So for the x squareds, on the left, there's just one x squared. On the right, I have 2a. I'm just going to make a little check mark when I use these so I make sure I don't forget anything. Plus b plus 2c. For x to the first, on the left I have 2. And on the right, I've got 3a plus 2b minus c. And then finally, the constants. On the left, I have negative 1. And on the right, I've got negative 2a. And I think that's everything. I just like to check these off as I go just to make sure I don't miss any as I kind of do this. The bigger the problems get, the easier it gets to miss stuff. All right. Once again, this isn't terrible to solve by hand. You can already see that a is 1/2. But I'm going to go ahead just for speed and put this into my poly-sci mode. This time I do have 3 equations and 3 unknowns. And my first equation would be 2, 1, 2, and that's equal to 1. My next equation, 3, 2, negative 1, and that is equal to 2. And my last equation, negative 2 for the A, 0 B's, 0 C's, and that's equal to negative 1. All right, solving that, I get A is 1/2, B is 1/5, and C is negative 1/10. So, using those values for my fractions, let's go back and rewrite our integral. A is 1/2, and in fact, I often like to pull the constants out in front. I didn't do it last time, but I will this time. So if the 1/2 comes out in the front, that's just 1 over x. B is 1/5, and then that becomes 1 over 2x minus 1. And C is negative 1/10, and that one becomes 1 over x plus 2. Right, so let's see here. That's going to be 1/2 natural log x plus 1/5 times. This time, again, I'm going to think through the u substitution in my head. If it helps you to write it out, certainly feel free. But u would be that denominator, and so the derivative would be 2. I'll have to compensate with the du with a 1/2. And then I can have the natural log of 2x minus 1. And then I've got minus 1/10. And here the derivative is just 1, so no compensation, just the natural log of x plus 2, plus c. There really isn't a whole lot to do here. I'll show you one small algebra trick. Again, other than maybe making that a 1/10, this would be pretty much a fine final answer as far as I'm concerned. But just a quick note. If you wanted to algebraically play with this and go a step further, then in 1/2 ln x, there's not a whole lot I can do with that. I could play with it a bit more, but I'm going to leave that there. This 1/10, right, that's a 1/10 and that's a negative 1/10. So if I factored out a 1/10, I'd have ln 2x minus 1 subtract ln x plus 2. See, putting that 1/2 up there, that would be the natural log of square root x plus this, because of the subtraction, would be a quotient rule. So the natural log of putting the 1/10 up would make that a 10th root. And the quotient would be 2x minus 1 over x plus 2. And that would also be a perfectly good answer, right? We could have even gotten a common denominator and made that 5/10 and gone a bit further. There's all kinds of things you can do to play with these. I just want to make you aware that sometimes answers that look slightly different than yours or even quite different than yours may actually still mean the same thing. So don't stress over that. All right, so that's the most general case. It's the situation in which we've got all different linear factors when we factor our denominator. There are two other cases I want to look at. The first one is the case of repeated linear factors. When we have a repeated linear factor, we have to build up to it. So if I had x minus r to the m power in my denominator, notice I don't just have the term something over a minus r to the m, I also have terms for all of the powers less than that. Let's take a look. This denominator, first of all, if I factor out the x, I'd have x squared plus 2x plus 1, which is x plus 1, or x plus 1 squared. So when I go to create my partial fractions, first of all, I'm going to have a fraction over x, so just a over x. And then for this x plus 1 squared, first I'll start with b over x plus 1 to the first, and then I'll go to c over x plus 1 squared. If this had been a third power, I would have had a plus d over x plus 1 cubed. I just start with the first power and build my way up to the highest power that I have. All right, we got to solve for the a, b, and c. So again, I'm going to clear my fractions by multiplying by the LCD. X times x plus 1 squared. And that's going to cancel with the entire denominator on the left, just giving me 1. Over here on the right, I'll have a times x plus 1 squared plus b times x times 1 of the x plus 1's plus c times x. This, remember, is just x squared plus 2x plus 1. So when I go to distribute, I would have ax squared plus 2ax plus a, and then plus a bx squared plus bx plus cx. Once again, I've got 3 types of terms: x squareds, x to the firsts, and x and constants. So I'll split those up and talk about them each separately. X squareds, there are none of them over here on the left-hand side. But on the right, I've got a plus b. X's, again, there are none of them on the left. But on the right, I've got 2a plus b plus c. And finally, constants. On the left, we've got 1, and on the right, we've got a. So again, I already know that a is 1. It wouldn't be that difficult to go back and solve this by hand, but just for simplicity, let's go ahead and plug this in. We've got 3 equations and 3 unknowns again. My first equation, 1a, 1b, 0c equals 0. Next equation, 2a, 1b, 1c equals 0. And the last equation, 1a, 0b, and 0c equals 1. And it looks like a is 1, b and c are negative 1. So, rewriting my integral, a is 1, so that's just 1 over x. B is negative 1, so actually I'm going to make that a minus the integral of 1 over x plus 1 dx. And same thing here with c, that's actually a minus 1 over x plus 1 squared dx. So integrating is going to give me the natural log of the absolute value of x minus, notice here no correction factor, right? The derivative of x plus 1 is just 1. So if I were to let u be that denominator, no correction would be necessary. I'll just get the natural log of x plus 1. And be careful here. You get so used to doing those natural logs when you do these partial fractions. But if you've got a power in the denominator, that is not a natural log. Let's do this piece with a little u substitution. If u is x plus 1, du is just 1 dx. So I have minus the integral of 1 over, that would be u squared, du. Or in other words, that's really u to the negative 2, right? So I'm going to integrate that with the power rule. That would be u to the negative 1 divided by negative 1 plus c. And I'm going to go ahead and combine those. Because it's subtraction, that would be the quotient rule for logs. So that I'd have the log of x over x plus 1. Minus a negative is plus. U to the negative 1 is 1 over. And the u is x plus 1. Plus c. So there's my repeated linear factors. There's one other type of problem that I want to take a look at. So far, everything that we've done has factored into linear factors. However, we know that there are some quadratics that don't factor. We call them irreducible. And I want to look at what happens when we have an irreducible quadratic factor. Two cases we're going to have to consider, what we call simple and repeated. So simple means there's just one, and then again the repeated, just like the repeated linear ones that we've just been doing. If we have a simple, single irreducible quadratic factor, like ax squared plus bx plus c, and I can't factor it, then instead of just a single value like b in the numerator, I actually put a whole linear expression, ax plus b, or whatever letters I happen to be on, in my numerator. And that's how I'll handle those irreducible quadratics. Okay. So let's give it a try. This first one, that denominator, if I factor out an x, is x squared plus 1. And I can't factor that any further. So I'm stuck with that irreducible quadratic. So my partial fractions decomposition, I take my original function, and first of all I'm going to say a over the x, just like I would have before. But then, for the x squared plus 1, because that's quadratic, the numerator is going to be linear. I happen to be on the letter b, so I'll go with bx plus c up here. So a linear denominator just gets a constant on top. A quadratic denominator gets a whole linear expression on top. All right, I once again want a clear fraction, so I'll multiply by the common denominator, x times x squared plus 1, which is going to divide out with the entire left-hand denominator side. And so I get the x minus 1 over here. And that will equal a times x squared plus 1 plus bx plus c. The x squared plus 1's cancel, so just times x. So I have x minus 1 equals ax squared plus a plus bx squared plus cx. We'll set up our system of equations like we've done before. For the x squareds, none on the left, and on the right I've got a plus b. For the x's, just 1 on the left, and just c on the right. And for the constants, negative 1 on the left, and just a on the right. So it looks like I already know both A and C. If A is -1, B is going to have to be +1 to add up to 0. So I won't even bother putting this one in my calculator. It was too easy. All right, let's rewrite our integral. I will have A over x, so that would be -1 over x. And then bx plus c. B and c are both 1, so just 1x plus 1 over x squared plus 1 dx. This is minus the natural log of x. And here we're going to go back to a trick we've learned before. I'm going to split up that fraction into two separate fractions by splitting the numerator. Think of this as the integral of x over x squared plus 1 added to the integral of 1 over x squared plus 1. This one I can do with a u substitution. If I let u be the denominator, du will be 2x dx, and I'll divide the 2 over. And I've got my x dx right there. So let's see. I'm going to have 1 over u, and then instead of x dx, I'm going to put 1/2 du. And I'll finish this one in just a minute. Let's finish the integral we're on. Integral of 1 over u would be natural log u, and my u is x squared plus 1. All right, this last one, actually I can do just by pretty much looking at it, or at least looking at it. I'm sorry, I did that last step, and you can just barely see it. Move that a little. There we go. This last integral, the one I haven't dealt with yet, we really just have to write down the answer. It's one of those that we know or we have if we just look it up. That's that arctangent, right? If the a is 1, then I'm going to get just 1 over 1 times the arctangent of x over 1, or in other words, arctangent x. Plus c. Since these have different coefficients, I'm not going to bother even trying to combine these. You can play with it if you want to, but I'm just going to leave it like that. All right, one last example, but fair warning, it's a little bit of a doozy. A repeated quadratic factor. Okay, so here we go. The denominator here was very kindly already factored for us, so all we have to do is set up our partial fractions. Let's start with a over x, the boring part. Also the easy part, right? Now because I've got a quadratic factor here, this x squared plus 1, I will have to have the linear numerator, bx plus c. And then just like we did with the repeated linear factors, I have to build my way up. I'm going to start with x squared plus 1 just to the first power, and then I'm going to add another term. I'm up to dx plus e now, with the x squared plus 1 to the second power. So, lots of variables to solve for this time. Multiply everything by the LCD. And on the left, the whole denominator just cancels out. And on the right, a will be multiplied by x squared plus 1 squared. That bx plus c multiplies this x and one of the x squareds plus 1's. And that dx plus e just multiplies the x. All right, bear with me as we crank through some algebra here. Let's see, I'm going to go ahead and square this out. That would be x to the 4th plus 2x squared plus 1. And let's see, I'm going to go ahead and I'm going to leave the bx plus c the way it is for right now. And I'm just going to distribute the x here. Make that x cubed plus x. And I can distribute this x at the end, dx squared plus ex. So let's see, this becomes ax to the 4th plus 2ax squared plus a, little FOIL here, bx to the 4th plus bx squared plus cx cubed plus cx plus the dx squared plus ex. Just barely squeezing that in at the end. Whew. All right, we're ready to set up our systems of equations. Notice that we've actually gone all the way out to the 4th power out here. And so even though there's no x to the 4ths over here, because there are over here, I'm going to have to start with x to the 4ths. 0 on the left-hand side. Got a plus b. X cubed, got -1 over here. And I think just c on the right-hand side. X squared, got 2 here. 2a plus b plus d. X's, I've got -1 here. C plus E. And constants, +1 here. A. And that's it. I won't take the time to make you watch me plug all this in. It's actually not even all that bad to do by hand. But I'm going to tell you, if you deal with all of this, calculator or even by hand, you end up getting the a equals 1, which we already knew here, of course. B is -1, pretty obvious from that equation anyway. C is -1, says so right there. D turns out to be 1. And E turns out to be 0. All right, let's put it all in. I have the integral of a over x, just 1 over x, plus bx plus c, -1x minus 1, and that's over x squared plus 1, plus dx plus e, it's just 1x plus 0, over x squared plus 1 squared. All right, where are we going from here? That one's simple, just the natural log of x. And then I'm going to split my numerator here. I'll have a minus the integral of x over that denominator, and then a minus the integral of 1 over x squared plus 1 plus the integral of x over x squared plus 1 squared dx. Right. Here, if I do a u substitution and let u be the denominator, du is 2x dx, and 1/2 du would be x dx, which I have right here. So I'm going to have the integral of 1 over u, and the x dx gets replaced with a 1/2 du. So I'm going to have a minus 1/2 natural log u, but u is actually x squared plus 1. Minus. This one I can just do directly. That's that arctangent integral again. So arctan x. And this one, I can actually use that same u substitution, right? So I'm going to have the integral of, let's see, the x dx is the du. So that is 1 over u squared. And x dx actually is 1/2 du. So I'm going to end up with a plus 1/2. That's really u to the negative 2. So the integral would be u to the negative 1 over negative 1 plus c. And I'm just about there. Let's see, that'll become a minus 1/2. And that actually, that u goes in the denominator since it's negative 1. So I'm going to put my u down on the bottom. X squared plus 1 plus c. And that, well, I was going to say it looks good. I don't know how good it looks, but it looks done. And that's a good thing. All right, that brings us to the end of section 7.4. 5.